Hello, in this lecture we are going to start magnetism, and we will discuss some type of magnetic materials in this lecture. And before proceeding the type of magnetic materials, we will discuss some simple terms like permeability. Permeability have a relation between magnetic field and magnetic field intensity or auxiliary field. H vector is nothing but auxiliary field or magnetic field intensity, and there is one more relation between mu and mu naught mu r, or we can write mu r equals to mu divided by mu naught. Mu naught is nothing but permeability of free space and mu r is called a relative permeability. Then we define magnetization, and magnetization is nothing but magnetic moment per unit volume, and it is denoted by capital M vector, and magnetic moment is denoted by small m vector. Okay, and the relation between magnetization and auxiliary field is given by m vector equals to xi into h vector, and here this proportional constant is nothing but susceptibility, and basically susceptibility is degree of magnetization in response of magnetic field. So if a material have high susceptibility, it means if we put this material in external magnetic field, then it will be magnetized more. More susceptibility means more magnetization. Okay, now discuss the classification of material, but before discussing the classification, I would like to explain some simple points. And let a simple atom, this is nucleus, and electrons revolves around it. Okay, so what is happening here? The first one is, as we know that electron also spins on its axis, that it means electron also have a motion on its about its axis, and that is called spin of electron. Second one is orbital motion of electron, because electron revolves around the nucleus. And the third effect is due to external magnetic field. As we know that nucleus have positive charge and electron have negative charge, so Coulomb force between nucleus and electron provide centripetal force to electron for moving around a nucleus, that is for circular motion. But when we put this atom in external magnetic field B vector, then there in that case electron experience Lorentz force too, and Lorentz force is nothing but q v vector cross B vector. And due to the Lorentz force, centripetal force on electron may increase or decrease, and you have already studied it in your lower standard classes, like in Bachelor of Science, I mean graduation courses, may increase or decrease, and that topic is called Larmor frequency. Okay, I hope you remember that topic, Larmor frequency. We also discussed this topic here. Okay, So here all 3 points I have told you, and these 3 points are responsible for any type of magnetic property. Now come to the classification of magnetic materials, and the first one is diamagnetic material. The second one is paramagnetic material, and the third one is ferromagnetic material. Okay, so let us discuss all the type of materials one by one. So let me tell you one thing, that here are 3 points, 1, 2 and 3, and the third point, centripetal force on electron may increase and decrease due to external magnetic field, is responsible for the diamagnetic property of any material. So basically diamagnetic property is found in all the materials, but the first two incidents, the first two motion, spin of electron and orbital motion of electron, are responsible for the paramagnetic properties. Okay, so the materials in which these two properties are more strong in comparison to the third one, they are a paramagnetic or ferromagnetic, but the materials in which the third property is effective in those materials, they will show diamagnetic property. So what happens in diamagnetic, what happens in ferromagnetic and paramagnetic, we will discuss. So the first thing, in diamagnetic material repels the field of lines, I'm talking about magnetic field of lines. Okay, so what happens if we put a diamagnetic material in external magnetic field, then magnetic field of lines will bend and will pass through like this. They will not pass through the material. Field of lines will be bend and avoid to passing through the magnetic material. While in paramagnetic material, if you put a paramagnetic, this is diamagnetic, this is paramagnetic, if you put a paramagnetic material in external magnetic field, then external magnetic field will be attracted and will flow like this. Okay, so attract the field of lines, and again I'm talking about magnetic field of lines. Okay, and the ferromagnetic materials are just like paramagnetic materials, but attracts more strongly. Okay, more strongly in comparison to paramagnetic materials. So this is ferromagnetic materials, so it will attract more and will allow more magnetic field of lines passes through inside the material. Okay, the next point is, if we put diamagnetic material in external, we put diamagnetic material in non-uniform field, diamagnetic material will move from high intensity to low intensity. Okay, because they repel the field of lines. Paramagnetic materials will move from low intensity to high intensity. If we put paramagnetic material in external field of lines, then paramagnetic material will move from low intensity to high intensity. And as we know that ferromagnetic materials have strong properties of paramagnetic materials, so they also move from a low intensity to high intensity quickly, or you can say more fast in comparison to diamagnetic materials. Okay, now let me discuss some more point. For diamagnetic material, xi is negative, and basically this is from -1 to 0. And for perfect diamagnetic, xi is -1, and we know the relation between xi and relative permeability, so we can easily find out by this relation. Okay, for paramagnetic material, xi is positive but small, so this is greater than 0 and less than 10, and this is not a sharp boundary that 11 will be a ferromagnetic. I am just using 10, just for a reference level. Okay, but xi will be small, but xi will be high and positive, like 100, like 100, 200. Okay, so I think you have understand the basic differences between all the kind of materials, and now let me explain the dependency of susceptibility on temperature. So for diamagnetic material, susceptibility does not change with temperature. This is for diamagnetic. For paramagnetic, susceptibility decreases with temperature, and this is inversely proportional to temperature for paramagnetic material. And for ferromagnetic material, this have a same characteristic after a temperature Tc, that is called Curie temperature, because after Curie temperature ferromagnetic becomes paramagnetic, and before T less than Tc, that is if temperature is less than Curie temperature, then the behavior of susceptibility for ferromagnetic is complex. Okay, so these are the basic ideas and characteristic of all the materials. But for the engineering student, especially for electrical engineering student, we further classify some more type of materials, especially ferromagnetic materials. So ferromagnetic material, characteristic of ferromagnetic material are explained by a domain theory, and domains are nothing but group of dipoles aligned in same direction in material. And who are the responsible for dipoles? Of course, free electrons. Okay, so for ferromagnetic material, we can understand this by domain theory, and this says that in ferromagnetic materials all the domains are aligned in the same direction, or you can say that in ferromagnetic materials magnetic dipole have tendency to align in same direction. That is why this is responsible for the strong magnetic properties of ferromagnetic materials, and the example are ferrum, cobalt and nickel. And we can further classify ferromagnetic material in two types, like soft and hard. Soft ferromagnetic materials are magnetized easily and also demagnetize easily, so they have a less hysteresis and less coercive force. But hard ferromagnetic materials are hard to magnetize and hard to demagnetize, have more coercive force. So basically these are basic differences. And susceptibility for soft ferromagnetic material is high in comparison to hard ferromagnetic material. Okay, now we discuss some more types, and here is antiferromagnetic material. And what happens in antiferromagnetic material? Actually there is tendency of electron, or you can say domain, to align in such a way that the total magnetic moment gets cancelled out. It means if in this direction magnetic moment have some value, then exactly the same amount of magnetization will be in the opposite direction, as you can see here. Okay, so in this case, practically susceptibility be equal to 1. Okay, susceptibility for antiferromagnetic material is 1, and you can see that net magnetization is cancelled out. That's why we called it antiferromagnetic material. And the last one is ferrite, or in some reference book or textbook, ferrites are also termed as ferrimagnetic, not ferromagnetic, but ferrimagnetic material. Ferrimagnetic. And ferrites are some exist between the ferromagnetic and antiferromagnetic, between the ferromagnetic and antiferromagnetic ferrites exist. So what does it mean that ferrite exists in between the ferromagnetic and antiferromagnetic? Because for ferromagnetic, all the domains have tendency to align in the same direction. For antiferromagnetism, domains align in such a direction that net magnetic moment gets cancelled out. But for ferrite, they align opposite in direction as well, but they have a less intensity in one direction, so there will be non-zero magnetic moment. So that's why I'm calling ferrites exist between the ferromagnetic and antiferromagnetic. Here the length of the arrow is representing the magnitude of magnetization. So you can see clearly and say that in this situation net magnetic moment is not zero. In this situation net magnetic moment 0. In this situation net magnetic moment is maximum. So ferrites exist between the ferromagnetic and antiferromagnetic materials. Okay, so now we will discuss how the magnetism and magnetic moment in atoms arises. So as we have already discussed that magnetism arises due to spin of electron and orbital motion of electron. So first we will discuss about the orbital motion of electron, that this is nucleus and electron is revolving around it. Okay, let the radius of the orbit is small r. Then we know that the current is given by charge divided by time, and the charge on electron is nothing but equals to quanta of charge, and let the total time period of electron revolving in this orbit is capital T. Okay, and because the circumference is small, radius is small r, then circumference will be 2 pi r, and the time period will be distance divided by velocity. Okay, so here this is equation 1 and this is equation 2, and we know that charge on the electron is negative of E. Okay, so current will be nothing but minus E divided by 2 pi r and E. Let me term it as equation number 3. Now we know that magnetic moment is nothing, magnetic moment small m is nothing but I into area vector. Okay, so m vector is nothing but minus EV divided by 2 pi r and cross section area, and this is equals to pi r square for a circle. Okay, so let me simplify it, and we get minus EVR divided by 2. You can denote it by small m vector or by mu vector 2. This is all your choice, and let me name it equation number 4. Okay, so now you can remember that angular momentum is given by capital L equals to m v r, because in the situation velocity is always perpendicular to radius vector, and L is nothing but m r vector cross p vector, so r vector cross v vector, but r and v are perpendicular, so we get mvr. Okay, so from this equation I can write mu vector equals to minus evr into m and divided by m. Okay, now I can write minus e by 2m mvr, and mvr is nothing but angular momentum, so I can write let me define it. Okay, we cannot put vector sign on velocity vector, so I just put it like this. Okay, and we get minus e by 2m and L, and if I want to write in the vector form, then I can write mu vector equals to minus e L vector divided by 2m. Why I cannot put vector on velocity? Because angular momentum is perpendicular to the both radial vector and velocity vector, so you cannot put vector on the velocity, but you can put the vector on L vector. Okay, so this equation also reminds us that magnetic moment is in opposite direction of angular momentum. Okay, so when I was in lower standard, I also got confused with this statement, and the question is why? Because the current is basically dimensionless quantity, so if I took here I equals to e by t instead of minus e by t, I will not get a negative sign here. Then how I can write this statement? Okay, so let me explain to you this. As you know that angular momentum is defined by r cross v. Okay, so you can assume that electron is moving in anti-clockwise direction like this. Okay, and in this situation angular momentum direction of angular momentum can be found out by right hand thumb rule, and if you curve your finger in anti-clockwise direction, then thumb will be in upward direction, and that is the direction of L vector. But the direction of current will be opposite, because current is always in the reverse direction of electron. So current is in clockwise direction, and you know that here m vector is I into a vector. So magnetic moment is direction of magnetic moment is given according to the direction of cross section area, and direction of cross section area is decided according to the current. So if you curve your finger around the current, then thumb will be in downward direction, so cross section area will be downward, and thus way m vector will be in downward direction. So I hope you have got my point, that always L vector and m vector are going to be in opposite direction. So there is no need to put a negative sign here. You can write this statement with the interpretation. Okay, so this is an important result, and let me name it equation number 5. Okay, now in quantum mechanics, angular momentum L vector is given by h cut under root L plus 1. Okay, h cut is nothing but Planck constant, and L is nothing but quantum number, okay. So mu vector can be written like this, minus E h cut divided by 2m under root L plus 1. Okay, I think you have studied one different form of a magnetic moment, because using Bohr's law, Bohr postulate, sorry, we know that angular momentum is integer multiple of h cut, and in lower standard class we read this form. So we put minus E by 2m, and for L vector we put n into h vector, h cut, okay, n h cut. So this becomes minus E h cut by 2m, and here comes some value of n, and these are same form, nothing is different. This quantity is called Bohr magneton, because this quantity is dimensionless. So basically this have dimension of magnetic moment, and this is quanta of magnetic moment, you can call it quanta. So this is called Bohr magneton, and it is denoted by mu b, and this is nothing but minus E h cut by 2m. And by putting the value of E, H and M, here M is mass of electron, you can obtain the value of Bohr magneton, okay. And the value of Bohr magneton is 9.27 into 10 raised to the power minus 24 ampere into meter square, okay. You can easily calculate it, okay. So we have obtained the formula: magnetic moment mu b, sorry, let me write only mu, minus E h cut divided by 2m L plus 1, and this quantity is going to be in under root. So I can write it like this, and this is because of orbital motion, and similarly we can write the equation for spin motion of electron. Here mu spin, and this is nothing but minus E s vector divided by 2m. Here s vector is nothing but spin momentum, or you can say that angular momentum due to spin, angular momentum due to spin motion, okay. But here comes another factor, Gs, and this is called Landé factor. Gs is called Landé factor, and for electron the value of Landé factor is approximately 2. So we can easily find out the magnetic moment due to spin of electron, because this will be minus 2 into, you can put the value of s vector. S vector is nothing but h vector into under root s plus 1, and s is nothing but spin of electron, and spin of electron is nothing but half. So you can easily find out the value. So minus 2, and I can write in the form of Bohr magneton, and this will be half and half plus 1, and it will be under root 3 times of Bohr magneton, okay. So this is the value of magnetic moment due to the spin of electron, okay. Now I'm going to tell you some more concept to find out the magnetic moment of atoms because of orbital motion and as well as spin motion. So in the lower classes, especially in school grades, you have calculated the magnetic moment due to spin only, and it is given by a formula which have a form like this, I think. And here n is nothing but number of unpaired electron, but here I'm going to give a general formula for magnetic moment, which include orbital motion as well as spin motion for any type of atom, and this is given by mu j vector. You can put a mod sign. Gj is nothing but Landé factor E h cut divided by 2m and under root j plus 1, and j is nothing but angular momentum, and this is basically net angular momentum, that is the total effect of orbital motion as well as spin motion. Okay, so what is the value of Landé factor? You have to remember this expression, and the Landé factor is given by 1 plus j plus 1 plus s plus 1 minus l plus 1 divided by 2j plus 1. Okay, so first you have to find the value of Landé factor, and you can easily find out then magnetic moment for any type of atom. Okay, now let me tell you some more basic things. Okay, so for atoms having electrons less than half filled shell, j vector is using like this, and for atoms having electrons more than half filled orbit, I think we should call it orbit rather than shell, orbit, then j is given by L vector plus S vector, and this is the basic difference, because if you write the value of j wrong, then you will find out the value of Gj and mu j also wrong. So you have to remember these two things. Now maybe you will think about the half filled atoms, then for the case of half filled atoms, L always will be 0 and J will be equal to S. Okay, J will be equal to S. So in this case you can easily find out the value of Gj, and it is going to be 2. You can easily find out it here. Once you put L equals to 0 and J equals to S, then in that situation this term will make 1, and 1 plus 1 become 2. Okay, now let me discuss some examples. Okay, like any atom like 3 plus valency, and we have to find out the magnetic moment for this atom. Then electronic configuration for the outer shell is given 4f3 5s2 5p6. okay, so here f is half filled, and basically it is less than half filled. Okay, so now you know that for f there are 7 subcells. Okay, and let me tell you some thing about quantum numbers. So n basically number of cell, as here this value is n. Okay, these are n. L is basically nothing but given by s for s orbit 0, for p orbit 1, for d orbit 2, and for f orbit L is 3. ml is given by from minus L to plus L, and ms is minus half or plus half. Okay, so here we have 3 electrons, so we can fill the 3 electrons like this, and the value of L in the formula of Gj here is given by summation of ml, and for f, as you know that capital L is 3, so this is 3 2 1 0 minus 1 minus 2 and minus 3, so we get here L equals to 3 plus 2 plus 1, so L is nothing but 6. Okay, and spin is nothing but there are 3 electrons, so 3 by 2. Okay, so J is given by L minus S because it is a case of less than half filled, and you can see here for the electron less than half filled we use L minus S. Okay, so 6 minus 3 by 2, that means 9 by 2, and now you can easily find out the value of Gj, and Gj is nothing but 1 plus Jj plus 1, so 9 by 2 and 9 by 2 plus 1, S plus 1, so S is 3 by 2 and 3 by 2 plus 1, minus L plus 1, L is nothing but 6, so 6 and 6 plus 1. Okay, and divided by 2j, j plus 1, 2 into j plus 1, and you can easily solve this. I am writing it directly, and this value will be 1 minus 0.27, that is 0.63. please check it using calculator, or you can do it simply. And now we can find out mu j, and which is nothing but Gj under root j plus 1, so this is 0. This is going to be 73. Okay, my mistake. 9 by 2 and 9 by 2 plus 1 mu b, so this value will be 3.63 mu b. So this is total magnetic moment for the NB having a 3 plus valency. Okay, similarly you can do some more examples.